All right, let's go ahead and talk about the self-ionization of water. And to understand pH, which our next set of notes are going to be over pH, we need to understand what the self-ionization of water is. This is going to be a really, really important concept when we start talking about pH and titrations. All right, so to understand whether a solution is acidic or basic, we'll use pure water as a neutral starting point. And so we say pure water is neutral because it's sort of arbitrary that we call it that, but we just call it neutral to compare it to other things. So although pure water is mostly water, if you do conductivity tests, you'll see that it does conduct a small amount of electricity. And I know that I actually said that pure water doesn't conduct electricity, but it actually does conduct a very, very small amount of electricity. What this means is that there are ions in pure water, and so those ions come from the self-ionization of that water. And so let's go ahead and take a look at what that is. And so the self-ionization of water is where two water molecules interact with each other in such a way to produce a hydronium ion, which is a H3O plus ion, and a hydroxide ion, which is the OH1 minus. And so here's two representations of what that looks like. The top one is the one that I'm going to focus on here. So notice it's two water molecules interacting with each other to produce a H3O plus and an OH minus. And essentially what happens is the hydrogen of one of the water molecules will transfer to the other water molecule. And so you do end up with a hydronium ion and a hydroxide ion. Now another way of thinking about it is thinking of one water molecule that where the hydrogen ion separates from the hydroxide ion, and you think of it as adding a hydrogen ion to the solution and a hydroxide ion to the solution. But again, the top one is probably the best way to think about it. So the self-ionization of water produces equal amounts of hydrogen and hydroxide ions. And at 25 degrees Celsius, the concentration of each of them is 1 times 10 to the negative 7. Now that's a really, really small number because that's a 0.000001, it's 6 zeros, molar concentration of hydrogen ion and hydroxide ion. And I'm going to go back here because again, notice how one water molecule will produce one hydrogen ion and one hydroxide ion, and so it has equal amounts of hydronium and hydroxide in pure water. Now because these ions are equal, we say that the water is neutral because we have equal amounts of hydrogen and hydroxide. Now the equilibrium constant, so the K value for the self-ionization of water, is 1 times 10 to the negative 14. And this number is going to be very important for this set of notes and for future sets of notes. And so we call that equilibrium constant Kw. The W stands for water because it's the self-ionization of water. Now, the way that we derive Kw is by multiplying the concentration of the hydrogen ion by the concentration of the hydroxide ion. So the hydrogen ion, the hydronium ion, times the hydroxide ion will give you Kw. This equation here is extremely important because what will end up happening is when we add an acid to solution or when we add a base to solution, you're going to be changing the amount of hydrogen ion and hydroxide ion. And if you add an acid to solution, a hydrogen ion, or you add a hydrogen ion to solution, what will end up happening is to reach equilibrium, to maintain that K value, you'll end up changing the amount of hydroxide ion and vice versa. And so that's kind of what the next set of notes is going to be about. So this equation is very important. And so notice that the equilibrium expression of Kw does not include the reactants. And that's because when we set up K values, as it's what was said in your equilibrium notes, you don't include liquids or solids in the K value expression itself. H2O, both reactants of H2O are liquids, so you don't include liquids in the K expression, and that's why you end up with just the concentration of hydrogen ion multiplied by the concentration of hydroxide You do not divide it by the concentration of water because it's a liquid and there's not really a concentration of it. So also, remember that K value that is less than 1 indicates that there is a lot of reactant. A K value of 1 times 10 to the negative 14 is a very, very small number, which means that water is almost entirely water. It's mostly water. There's very little hydroxide and hydronium ions in solution. Also, this is an endothermic process. We've learned about endothermic and exothermic reactions next unit. But essentially what that means is that it requires energy to occur. So if it's going to absorb energy for that to occur. And so if you change the temperature of water, you're also going to change the Kw, the K value of water. And this is actually true for most chemical reactions. K values are at specific temperatures. And if you change that, you actually end up changing the K value of a reaction. So that's it. The important thing here to note is that there are always some amount of hydrogen ion, there's always some amount of hydroxide ion, and we're going to see in the practice problem that because we have the Kw, we are able to calculate the amount of hydrogen ion if we know the amount of hydroxide ion and vice versa. So we're going to use that in our guided practice problems to do that. So go ahead and watch the guided practice problem video and come to class with questions, and you guys have a great day.